guys, and welcome to this first video about bonding. We're going to be looking at bonding and different types of bonding, including Vesper theory and all kinds of other areas. Alright, for our beginning introduction here to looking at ionic compounds, so I have potassium chloride here, and I want to do this dot and cross diagram. The first thing we got to look at, well, what the heck is so potassium? I have a K, and if we know potassium is in group 1A, therefore it only has one valence electron. So I know potassium has my one dot. Well, chlorine, okay, chlorine's a group 7A element, so therefore it has 7 valence electrons, and I'm going to use crosses and we got 2 on each individual side, and I get a cross here. All right, so what really happens is then potassium and chlorine, neither one of them are completely satisfied, have their full octet. Potassium, we know, wants to give one away. Chlorine would like to take one. So they get this shared electron pair here and end up with, and I can show it either this way, or sometimes we show just potassium with nothing on the outside, and we can show it with like this, potassium with a +1 charge, and we also have chlorine now, which has its X's, and then the dot from chlorine with a -1 charge. And so now I have my full satisfied potassium chloride. All right, same way here for sodium oxide. If I wanted to do sodium oxide, all right, which we know is a group 1A element, and oxygen, which is a group 6A element, so therefore oxygen has 6 valence electrons, sodium has 1. We know that sodium in the ionic formation wants to give its electron over to oxygen. Well, there are 2, so I have to draw out, okay, we're going to draw out sodium, and I have also another sodium, with both of them being +1, so a total of +2. And I'm going to use this sodium as being a dot, and this sodium is circle. And now oxygen, okay, it had 6. I'm going to use my crosses. All right, we know that one of these sodiums has to be here, and that's my dot. And the other one has to be my circle. So filling in both sodiums, each sodium giving up 1 valence electron. So therefore oxygen can now have its full octet. And we are completely satisfied there. All right, so here we're looking at, once again, looking at the next one, at calcium oxide. So if I want to go down here to calcium oxide and look at that, so I have calcium, which is a group 2A element, so therefore we know that normally if I looked at just its outside ring, if I put just its outside ring there, we would have 2 electrons on the outside ring of calcium. Right? If I was looking at oxygen, put oxygen in the center, on the outside ring of oxygen we would have 6. Oxygen, because oxygen is a 6A element, and therefore it needs 8 to be a full octet and be completely satisfied. All right, so what's going to happen here? We know that calcium in the ionic formation is going to donate or give, it's actually going to give its electrons over to that. It's completely empty on the ring because it has given it over to oxygen, and that makes a +2 charge formation. And oxygen on its now has the full 8. So we have we have 2 circles from the calcium, showing that this is a -2 charge, and now we have the ionic formation, dot cross ionic formation for calcium oxide. All right, so go ahead and try the last one, magnesium chloride, and see what you get. All right, so now we're looking at covalently bonded molecules. Well, what do we know about covalent bonded molecules? We know they have to share their electrons. So sometimes they share equally, sometimes they don't. So we'll be talking about that later in the video. Well, covalent bonds are simply going to share to be able to satisfy, so there's no plus or minus charges. So let's look at this first one, tetrachloromethane, so CCl4. We have carbon, and we have 4 chlorines, and I'm just going to put the chlorines all around the carbon here. All right, so we know chlorine is a group 7A element, so I'm just going to put 7. All right, so now that I have all of these done and drawn out, we can look and see that at each of these bond sites, or each of these sites that we can see a little bonding going on, we can see here, so you can see at each location here, 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 and around each element you can count up 8 electrons that are associated with each one. So they've all fulfilled their octet. All right, so here it is phosphorus 3 chloride. Well, what does this little Roman numeral 3 indicate? Well, that's telling me they're kind of giving away the oxidation number or the charge for phosphorus, which normally does not do this, but they're telling me that this charge or oxidation number is going to be a +3, and that chlorine, since chlorine is a group 7A, chlorine needs to get one more, and so it often forms a -1 charge. Well, when you have charges, we can write our formula. We know that 3. So now that I know my actual formula, we can figure out what is going to be our dot and cross and how is that going to work. So we know I have 1 P, so I have a P in the center, and I'm going to have 3 chlorine somewhere around this thing. And my P I'm going to draw with red, and I'll do these with. All right, so you can see I have my phosphorus chloride. Now I have a bond pair here, a bond pair here, a bond pair here. Well, this bond up here on top of the phosphorus, so we're looking at this bond group up here at the very top up here. Those are not involved in any kind of bonding, so we're going to call those, they're called a lone pair. So they're not involved in the bonding, they're just alone. All right, so see if you can go ahead and figure out how C, D, and E work out and do those. All right, so here is C. We can see there's 7 electrons around bromine, 7 electrons around bromine. We get this bond or single bond in between the two. Beryllium, well, beryllium, we can see here's the green, these 2 valence electrons from beryllium. We get a connection there between these two. Now, phosphorus, this is a little weird molecule. We call this expanded octet, that they get a little bit different in here. Well, we can see that these aren't supposed to be connected, by the way. So in between these two, they're actually supposed to be separated like this, where the chlorines aren't touching. I just drew it badly. So we can see now, instead of like where it says when we had phosphorus chloride, where phosphorus had 2 lone pairs, now each lone pair here is kind of split up and joined in with an extra chlorine. This only happens under rare conditions. This typically only happens at very low temperatures that you can get this breaking of this lone pair bond. And this is called when you have so this is an expanded octet because phosphorus actually has more than 8 electrons associated with it. Phosphorus actually has 10 electrons. So because phosphorus has that available d orbital to kind of put extra electrons in as far as bonding, those elements can do those kinds of things. All right, so go ahead and try these couple as well. Doing the so here we have our compound ethene, and we're looking at how do I combine those. So let's go ahead and try to draw these dot and cross diagrams for a little bit more of our covalently bonded molecules and see how those work out. So try these 3A and B. All right, on those last couple on 3, if you want to just check in the back of your textbook and see how those work out for you, make sure you can get the right answers. All right, now we're going to look at something a little bit different. It's still looking at dot and cross diagrams, but now we're taking a couple of different compounds. So I'm taking the compound BF3 and the compound ammonia or NH3. Let's see, how is it possible that these two things are going to combine? All right, here, so for 4A, we have the diagram here for boron trifluoride. So boron we know has 3 valence electrons, so we have all 3 drawn here in red. We put our fluorines around 7 valence electrons, we have them around. Well, you can see boron is what we call electron deficient. It doesn't have all quite 8 electrons. Well, if ammonia is around, and ammonia can now donate, so we call it's going to actually donate both of its electrons over here, because ammonia has a couple extra. It has this lone pair over here around it that it can actually donate, and they can share, and it creates this coordinate covalent bond, or what they call in Cambridge, they call it, also sometimes call it a dative covalent bond. And we can show that with we get a bond between those two, and that answers part B as well. So go ahead and try for part double I and part B for that. All right, now the other part I want to show you, sometimes we also often indicate this, instead of doing this whole circle and dot thing, which can be sometimes cumbersome and time involved, we can just do boron, and I can show by line fluorine and fluorine. And so that's exactly the same thing as showing this shared pair in fluorine. We don't indicate any of the bonds that are in that lone pair configuration on fluorine. All right, but then we have this ammonia group over here, which is in the same basic configuration, H, and I show all the bonds using a line. And we can show that dative or that covalent bond, that coordinate covalent bond, that dative bond, where ammonia is shearing over to boron, and now we get that bond there as well. So you can show either way.